Green algae have a great potential to produce, to generate oils and other valuable products in a sustainable fashion. Oils produced by algae can one day offer a cleaner and much sustainable fuel to replace the current fossil fuels, such as petroleum, natural gases, and other resources, which power our modern civilization. In this project, our goal was to design a system where we can obtain the biomass from algae, which would yield to produce biodiesel, and we succeeded in doing that. So what is a bioreactor? A bioreactor is any device that is used to collect, to grow and collect biological materials such as proteins and cells, while maintaining an environment which would be suitable for that desired product. Traditionally, bioreactors were used to produce products for the health field. You can see here in this these are large-scale bioreactors that use transgenic E. coli to produce insulin. Our bioreactor is a specialized bioreactor which utilizes light for the production of the algae biomass. So after the algae is produced, we take that and dehydrate it or concentrate it and use it for further use, basically. Algae is environmentally friendly. It consumes carbon dioxide and releases oxygen with the minimum amount of resources. And the common uses of this, it comes in and basically creating solvents such as biodiesel or bioethanol. And the way this is done is through photosynthesis, which is a biological process that uses water, carbon dioxide, light to produce oxygen and release the biomass here. And later we take this biomass and process it into biodiesel or bioethanol.
So there are two types of systems. There's an open pond system and a closed system. The open pond system basically uses a large-shaped pond with a paddle wheel designed to maintain flow. The good thing about it is it's cheap, but it does have a poor environment control. As opposed to the open pond system, the closed system is an enclosed chamber that is supplied with nutrients and a light source. The advantage of that is the ability to recycle your nutrients. Bad thing about it is it has a high startup cost, but it does have more algae per volume. So we use the closed system because we were able to control the growth environments. We use cylindrical geometry for our chamber because it had the highest biomass yield as opposed to other geometries. Now with the deprivation of nitrogen, the algae had no choice but to store its lipids. We used LED as our lighting source because it's more energy efficient, and we also, with the use of the flexible LED lights, we were allowed to have even distribution of light. So why algae? Algae has shown to yield 10 times more gallons of oil per acre per year than other traditional crops like corn and palm oil. In our system, we used Nanochloropsis as our strain of algae, since it can survive in a wide ranges of pH and temperature environments without causing any kind of negative growth. It's been also proven to have high lipid yield compared with other algae strains. Now, we used red and blue lighting. The Nanochloropsis predominantly has chlorophyll A as opposed to B, and due to the nature of chlorophyll A, as seen here on this chart, it has the greatest absorption around the wavelength spectra of blue here and red over there. So we didn't use green light since it wasn't utilized by chlorophyll A. Also, we save more energy by eliminating green light. We do have a demonstration video of our project.
Alright, so this is our algae bioreactor. This is the reactor itself, wrapped with some flexible LED lighting, and we have that set up on the stir plate here with the stir bar to make sure that things keep moving around. There's no dead zones, no stagnation, everything keeps moving. Also, something that will help in the mixing is we have this ruler down here that is CO2 to the algae, which is essential for the photosynthesis and the production of lipids. Here we have our water that we collected from the Rouge, and this is our collection chamber for collecting algal growth that has already taken place. And it's set up with a siphoning system, so as we add water, as we add water from here, water will be collected at the same rate in our collection bucket.
Okay, so how do we create our biodiesel? We start by putting our algae in our bioreactor for 2 weeks. Then we use a mechanical press to separate the algae, and then we put them in a dehydrator to dehydrate them. From there, we add hexane to the dry biomass to help separate the lipids, and then we had to wait for the hexane to fully evaporate before we knew we had all the lipids separated. Then we had to do a transesterification from the lipids by adding ethanol and sodium hydroxide, and that will produce our biodiesel. Overall, we produced 5 grams of dry weight, and we had a 76.88% wet weight or lipid content of usable from that dry biomass. In the end, we produced 4.5 milliliters of biodiesel, and we know it's biodiesel because the color of our biodiesel is comparable to that of actual biodiesel. We then did test viscosity, and we fell into the range of biodiesel, as well as our density was only 2.4% off that of actual biodiesel. And then before all these tests, we did predict what we would get, and typically you receive about 60% lipids from your biomass, which would give us about 3.61 milliliters of lipids to use from that 5 grams of biomass. In our case, though, we actually ended up with 76.88% lipid yield, which gave us that 4.5 milliliters.
Alright, so in other published closed systems, similar in size and scale to ours, they were only able to produce about 0.151 grams of lipids per day, the average over their entire growth period. With our system, we were actually able to produce almost double that, 0.275 grams of lipids per day on average, so definite improvement on existing systems. Furthermore, as Nick was saying, we got a dry weight that was 76% lipids by weight, and compared to other systems that use the same type of algae, the maximum that we saw them yield was about 60%, and furthermore, the highest we saw reported with any species of algae was around 77% lipids by mass. Some improvements we would like to make. We would like to be able to extract the algae from the water more efficiently. So some ways we could do that would be centrifugation rather than mechanical press. Also, we could pre-treat the algae somehow, perhaps sonication, so it breaks open the algae prior to extracting the lipids to make that process more efficient. So overall, we felt that we were able to complete our objectives. We were able to grow algae effectively with a high lipid content in our bioreactor, and we were then able to produce biodiesel efficiently with that algal mass. I would like to thank Dr. Gosher, our advisor, for his time and patience, and the rest of the bioengineering department. Thank you. Any questions? It's one of the most researched. It's very tolerant to a wide range of pH and temperatures without negatively affecting the growth, the lipid yield, that is. But yeah, so here you can see Nanoperopsis, and the high end has around 68% if you do things properly. So it has a very high lipid content compared to most others. That's why we chose it.
Vegetable burgers, my wife eats them, and if you look, they have low fat. The way they get the fat out of them is using hexane. So you probably don't want to eat them.
What was the most challenging part of it?
Most challenging part? Well, extracting the biodiesel was the hardest part. There's a lot of different methods for doing that, and there was a lot of ambiguity, if you will, with what the best way of going about doing that would be. And some of them are very resource intensive, and we didn't have the time or money to do some. I think that could be more efficient. The biodiesel? You could.
I mean, what you made.
What you made? So what we made, we supplemented it with normal diesel at a ratio of about 20% biodiesel, because this is a lot more viscous than normal diesel would be, so you can't run it in an engine without modifications here.
You have a bucket.
We don't. We have a chemical tube over there.
The bucket was for the.
Oh, that's what you have.
The bucket was for the algae.
That's what it is.
Yeah.
You know how to get rid of it.
What?
I had a question. I may have missed